This is 2007 AMC 12B problem 23. How many non-congruent right triangles with positive integer leg lengths have areas that are numerically equal to 3 times their perimeters? Okay, let's just solve this problem by first drawing a random right triangle. That's right, random right triangle right there. Okay, so we know that the two legs can be like A and B, and the hypotenuse is going to be a squared plus b squared, square root a squared plus b squared. And it says that the area, which is AB over 2, is 3 times its perimeter. Perimeter is a plus b plus root a squared plus b squared. So that's that. That's our equation that we want to solve. And there's 2 variables, but no worries, we can solve it, and because it's a Diophantine equation, meaning all the solutions have to be integers. Let's first multiply both sides by 2 to get rid of this fraction over here, because we don't want to work with fractions. So we have 6. Let's expand the brackets. We have 6a plus 6b plus 6 root a squared plus b squared. Okay, so how do we factor this out? Because notice that we have AB, we have 6a plus 6b, so this looks like Simon's favorite factoring trick. But if we factor this out, we have this thing left, which has a root, so we don't really know what to do with that. So we want to first get rid of this thing, or we can simplify this part. But either we want to simplify the entire equation so that there's no square roots, or there's no AB terms, or something like that. Okay, so notice a squared plus b squared is just a plus b squared minus 2ab. That's a squared plus b squared, right? And both of these, and a plus b is over here. That's 6. This is 6 times a plus b, and ab is over here. So we can let ab equals s, and let a plus b equals p. So a plus b is p, right? So we have s equals 6p plus 6 times the square root of, so a plus b squared is s squared, or actually no, it's p squared. So that's p squared minus 2ab 2s. So how's this simpler though? Because we don't have the ab term, and also we don't have this 6a plus 6b thing. We only have one term, 6p. So now we can move 6p to the other side of the equation, and we can square both sides of this equation to get rid of the square root, because that's what we actually want to do. So we have s minus 6p squared, which is s squared minus 12ps plus 36p squared. And on the other side, we have 36p squared minus 72s. So the 36p squareds cancel out, and we have s squared minus s squared plus 72s minus 12ps is 0. So how do we move on? Firstly, notice we can divide all of these terms by s. So let's do that to simplify, because we don't want this quadratic term here. So now we have s plus 72 minus 12p equals 0. So this means that we can actually try and factor this out now. But how? Because we have s and p, and we're kind of stuck with 2 random terms and the random constant here. Well, remember s and p actually represent something in terms of a and b. Let's plug those values back in. S is ab, and that's ab plus 72 minus 12. P is a plus b. So if p is a plus b, that's 12 minus 12a minus 12b equals 0. So now we can apply Simon's favorite factoring trick, which is basically you first factor the a out. So now you have a times b minus 12 minus 12b plus 72 equals 0. And then you want to factor a number out of here, so that it's something times b minus 12. But if you factor out, so this means we want to add 72 to both sides, so that it's like that, and then you can have a times b minus 12 minus, if you factor out negative 12, you have b minus 12 right there. So now you can factor this out. It basically says a minus 12 times b minus 12 is 72. Which is indeed what we want, because now we can list out all the factors of 72 and find a and b, and find the number of solutions for a and b, because that's what the question says. We want to find the number of solutions for a and b. So, okay, so 72. Well, 72 is 1 times 72, 2 times 36, 3 times 24, 4 times 18, 6 times 12, 8 times 9. That's all. Okay, so when it's 1 times 72, A is going to be 13 and B is, so A is 13 and B is 84. And then we have A is 14 and B is 48. And then we also have A is 15 and B is 36. And we also have, we have A is 16 and B is 30. We have A is 18 and B is 24. We have A is 20 and B is 21. So all of these solutions work because as long as you apply the Pythagorean theorem, you will have the hypotenuse, so don't worry about the triangle inequalities and stuff like that. So let's just count the number of solutions. Notice we don't care about the order in which A and B are in because that we want non-congruent right triangles, and A and B are two sides. If you switch the sides, you get the same triangle. So the order doesn't matter. So let's count the pairs. We have 1, 2, 3, 4, 5, 6 non-congruent right triangles that work. So the answer is 6, which is A.